Hi everyone, so welcome to the start of chapter 2. We're going to start with 2.1, which is going to focus on perpendicularity. So you might know this already, but lines, rays, or segments that intersect at right angles are what's called perpendicular. So let's go through a few examples. So here I have line L and line M, and let's say that I told you that they formed a right angle. So what we could actually write to show that they are what's called perpendicular is we can write L is perpendicular to M. So this little upside down T is actually the symbol for perpendicular. In this example, I've got two rays, so ray PQ and ray PR. And let's say I told you again that they form a 90-degree angle. So what we could actually write is we could put PQ is perpendicular to PR, or you can write them as rays as well. In this example, I have a line segment and a line, and we'll call this line L. So I could actually write that line segment AB is perpendicular to line L. So here are some examples of where right angles are going to be formed. And if AB is perpendicular to line L, then actually a couple things happen. All of these are right angles. So angle 1, angle 2, angle 3, and angle 4 are all right angles. And that happens because you've got straight lines, and straight lines are 180 degrees. So if this one is 90, well then 2 and 4 also have to be 90. And the same goes for 1. So that is why we have 4 right angles formed. So something that you don't want to do, and I've talked about this before, is do not assume that perpendicularity from a diagram. So maybe I could draw you this nice triangle, and it kind of looks like it's a right triangle the way that I drew it. But unless they're explicitly telling you or they put the little box, do not assume that there is a right angle here. We don't know what that angle measure is, and we're going to keep it that way unless we can prove it. So the most commonly used pair of perpendicular lines are the x and y axis, actually, something that you've been using for a while. So this is the horizontal is your x-axis, the vertical is your y-axis. They form a right angle. And if you remember from algebra, we're actually dividing this x and y-axis into what are called quadrants, and each one has a 90-degree angle. So this is quadrant 1, and then it goes in a counterclockwise motion. So quadrant 2, quadrant 3, and quadrant 4. And just in your textbook, it just gives you a little bit of a review that we call coordinates. Maybe you called them points when you were in middle school, but the x and the y are really called coordinates. And more specifically, right in the middle where the x and y axis cross is called your origin. And that point or coordinate is at 0, 0. So that's the most commonly used pair of perpendicular lines. Now, two lines that intersect but are not perpendicular. So maybe I've got this horizontal line here, and this line is coming in on an angle. So they're definitely not perpendicular. I'm telling you they're not. They are what's called oblique. Okay, so that's what we're going to call lines that are not perpendicular but intersect. And you probably already know, but parallel lines are lines that never cross, and more specifically, they actually have the same slope, and that's why they never cross each other. So those are our different types of lines. Perpendicular forms a right angle. We've got oblique that just cross each other, and parallel means that they are not crossing and have the same slope. And later on, we're actually going to get more into some parallel line theorems, but we're just going to focus on perpendicular lines for now. So let's get right into our proofs. So if you remember, the first thing that we do is we're going to draw our T-chart, and we are going to put an S for statement on the left and an R for reason on the right. And I told you that the first thing you should really do is you should look at your givens and mark up your diagram. So here I've got AB is perpendicular to BC. So that means that there's a right angle being formed. Same thing with DC and BC. So there's another right angle being formed. And then the first step of any proof is always to write out your givens. So AB will be perpendicular to BC. DC is perpendicular to BC. and we put our reason as given. So now our goal is to try and prove that angle B is congruent to angle C. So I'll give you a minute. See if you can figure out what will be the next steps in the proof first before we go through it together. So if you remember from chapter 1, we learned this thing called Theorem 1. And Theorem 1 said that if two angles are right angles, then they are congruent. Well, that's probably what I'm going to end up using here. However, you first have to state that you have right angles. So our second step in the proof is going to be angle B is a right angle and angle C is a right angle. And I can name them by one letter because it's not causing confusion to the reader. And the reason is because of, and this is a new reason, definition of perpendicularity. So this is exactly how we're going to write it. And this really just means that if two lines are perpendicular, then they form right angles. And this is actually reversible. So remember, we talked about how definitions are reversible. So you can also say if two lines form right angles, then they are perpendicular to each other. So now that we stated that we have two right angles, we can go to theorem, our third step, which is going to be theorem 1. So therefore, angle B is congruent to angle C because of theorem 1. So I stated that I had my right angles, and then I stated that they are congruent by theorem 1. And now I finish the proof. So try the next one. You're given that angle ABC is 90 degrees and DC is perpendicular to BE. Prove that angle ABC is congruent to angle DCE. So I'm going to mark up my diagram again. So I know that ABC is 90 degrees, so I'm going to put my box. And I know that DC is perpendicular to BE. So I'm going to put another box. Do my T-chart, statement, reason, and I'm going to put my givens first. So angle ABC equals 90 degrees, and DC is perpendicular to BE. And the reason is that it is given. Now, this is very similar to the top proof, right? I'm probably going to end up using theorem 1 again because I've got right angles. However, I first need to state that I have those right angles. Now, for angle DCE, I can state that that's a right angle because of definition of perpendicular, right? I'm told that these two lines are perpendicular, so therefore they must be forming a right angle. This one's different. This is telling me its measure, that it's 90 degrees. So I could put angle ABC is a right angle, not because of definition of perpendicular. I don't have that perpendicular symbol here. But we do know that if an angle is 90 degrees, it's a right angle. So if you remember from chapter 1, the reason here is definition of a right angle. So I'm stating the same thing, but the reasons are different, right? I'm stating this one based off of perpendicularity, and I'm stating this one off its measure with the definition of a right angle. So now my last step is just going to be to say that they are congruent to each other. And the reason is, again, theorem 1. If I have two right angles, they are congruent to each other. Besides proofs, you're also going to have to do some word problems. So this chapter contains some word problems that describe equal ratios, aka proportions. So you did proportions in algebra, and I think even in 8th grade. So these problems are just meant to help you be ready for this type of problem, because when we get to 2.2, you're going to be doing a lot of word problems. So let's look at number 1. The ratio of two numbers is 4:3. This is sometimes read as, like I said it out loud, 4:3 instead of using a colon. One of the numbers is 7 more than the other. See right now, if you can try this on your own, find both numbers. So as I would tell my students all the time last year, when you're given a ratio problem, take an X and put it right next to each of your numbers. So we know that one number is 7 more than the other. So it's not, the numbers are not 4 and 3, but they are in a 4-to-3 ratio. So I'm going to name them 4x and 3x. Now I'm going to set up an equation. So one number is 7 more than the other. Well, the 4x must be the one number, because if it's 7 more, it has to be bigger, and 4x is going to be bigger than my 3x. So I'm going to say 4x is, remember, is always equal, 7 more than the other. So the other is 3x plus 7. That's 7 more. So that's going to be my equation. That is this statement right here. Now it's just solving. So subtract 3x from both sides, and you get x equals 7. Now I have to plug x back in order to find the two numbers. So if I plug in x with the 4, I'm going to get 28 as my first number. And with the 3, I'm going to get 21 as my second number. And then just always go back and make sure that they make sense, right? If I was to take 28 over 21, would that simplify to 4/3? Well, I could divide the top by 7 and the bottom by 7, and I would get 4/3. And 28 is 7 more than 21. So this checks out and meets all the criteria. So here's another example. The ratio of two numbers is 5-2. The larger number is 6 more than twice the smaller number. See if you can find both numbers. So again, I'm going to throw an x next to each one. So I've got 5x and 2x. The larger number, that's my 5x, equals 6 more than twice the smaller number. So twice the smaller number means to multiply by 2. So 2 times my smaller number, and then 6 more than that. So that's going to be my equation from this sentence right here. Now I'm just going to solve. So I'm going to multiply to get 4x plus 6, subtract the 4x, and I get x equals 6. Now remember, that's not my answer. I have to plug back in. So I'm going to plug in x. So 5 times 6 gives me 30. 2 times 6 gives me 12. So those should be my two answers, but let's double check. If I do 30 divided by 12, or over 12, if I simplify these down, so I'll divide the top by 6 and the bottom by 6, you get 5/2. That checks out. The larger number, so the 30, is 6 more than twice the smaller number. Well, if I do twice 12, I get 24, and 6 more gives me 30. So that checks out. So that's how I would go back and make sure that your numbers work. So that's 2.1. When we meet next, we will start 2.2.